Good afternoon to all of you. Am I audible?
Sir? Yes, sir. Good
Okay.
afternoon. Sanjeev will welcome you, sir, soon. Begin in a minute.
I will wait for
Thank
the
you so
mic.
much, sir. So yeah. So good morning, everyone. Welcome to day 4 of this National Postgraduate Education in Homeopathy by Homeopathic Science Congress Society and Homeopathy 360 webinar, which is being supported by CCRH and all PG Homeopathic institutions of India. So we are trying our level best for you to explore and pave a new path for the homeopathy through this national webinar on PG education, discussing the research methodology, biostatistics, and various other topics which are being required and necessary being a homeopath to make homeopathy an evidence-based science. So I'm thankful to all the organizing committee members, Dr. Amit Sahani sir, Dr. Sanjeev Kumar sir, and Dr. Vivek Kumar Shell sir for being with us in organizing this webinar series, this grand webinar series of this year, and Dr. M.K. Sahani sir who has been the mastermind. So thank you so much everybody, and also I would like to thank Mr. Manish Jain, the director of Vision Publishers, who is working day in and out to promote homeopathic knowledge to the fraternity. And without wasting any more time, I hope everybody is aware of the Homeopathy 360 platform. So I would just request, we have our coordinator, the organizing president of this webinar series, who will be coordinating the event further. So I'll just welcome him to the platform and announce about and introduce him. I feel privileged enough to introduce sir. So thank you so much for coming, Dr. Sanjeev Kumar Singh sir. He is the Dr. Sanjeev Kumar Singh sir. He's the associate professor in the department in the department of repertory at GD Memorial Homeopathic Medical College and Hospital, and has completed his MD and BHMS, PGD, HMM from Symbiosis, and also he's the General Secretary of Scientific Standing Committee of Homeopathic Medical Association of India. So we welcome him, and I hand over the session to him, sir. Over to you, sir.
Thank you so much, Dr. Yasika. Thanks to Homeopathy 360 family, Mr. Manish Jain, and a special thanks to Dr. M.K. Sahani sir, man behind all this event and scene. So without wasting our time, I welcome all the delegates, participants, and our speaker of today's. We have two speakers, Dr. Partho Pratim Pal and Dr. Subranal Saha. And before that, our co-chairman is with us, Dr. Amit Nayak, Dr. Atul Singh, chairperson. He will join soon. Uh, Let me introduce our co-chairman, Dr. Amit Nayak. He is professor and head of Department of Materia Medica and academic in charge, State National Homeopathic Medical College, Lucknow. Is guest speaker at international platform and senior inspector in CCH, New Delhi. He is examiner in various universities as well as he has written a number of articles on different topics and often talked about more than 100 programs. He delivered the presentation in CME at Pandit Jawaharlal Nehru Homeopathic Medical College, Kanpur, as well as given the presentation in various events like presented seminar in Jabalpur Medical College. He was also invited by the Ayush Mission for giving the presentation in Ayush Kavach during the pandemic situation, as well for presenting lecture as a guest speaker in Homeopathy 360. So I welcome you, sir, and request you to say a few
Thank you.
words on this occasion. After that, we will come to our speaker and we will start the scientific session.
Okay.
Yes.
Thank you so much for that. So first of all, I would like to give many thanks to respected Professor Saini sir who invited me, and I also congratulate to entire team of Homeo 360, Dr. Manish Jain ji, Mr. Manish Jain ji, Dr. Yashika Roda for organizing such type of important webinar, which we can providing valuable informations of different topics. So people are just getting various kind of knowledge for implementing his knowledge not only in clinical practice but also in the academic profile. So today's topic is very, very interesting because everybody wants to know about the what kind of research we have to do. Because after Dr. Henneman, I'm sorry to say we have no good idea, not a good thought by which we can implement in our clinical practice. So this is very, very important, and this is very, very important topic, not only for the UG students but also the PG students, because research methodology, without research we cannot apply our medicine. And I would like to give many, many congratulations to entire team of Homeo 360 and Professor Dr. M.K. Saini sir for organizing such type of wonderful webinar to their students. So thank you so much for that. So I don't want to waste any more time. So over to Dr. Yashika.
Thank you, Dr. Amit Naik, sir. Now we are coming to our speaker, Dr. Partho Pratim Pal. He's very young and energetic speaker of this webinar today, and his topic is Introduction to Biostatistics. Let me introduce. He has completed BHMS from the Calcutta Homeopathic Medical College and Hospital, securing second position in West Bengal University of Health Sciences in 2011. Completed MD Home in the subject of practice of medicine from National Institute of Homeopathy in 2015. He joined CCRH as a research associate at DACRRI Kolkata in 2015. Became research officer as well as scientist in CCRH, with first posting at RRI Agartala, Tripura in 2016. Again transferred back to DACRRI Kolkata in 2018 as a research officer. Presentation in many national seminars with more than 30 publications in several reputed peer-reviewed index journals. He had practiced in Homeopathic Medical College as inspector on order from CCH. So I request Dr. Pratim Pal to present your research paper. Over to you, Dr. Pratim Pal.
Thank you, sir. And first of all, thanks to the whole organizing committee for allowing me, giving an opportunity to present my presentation in this platform, in this worldwide national platform. So thanks to Sani sir, to the chairperson, co-chairperson, and all of the people who are actually related with the organizing team. And without much wasting time, I would like to proceed with my presentation. So my topic, which I was given to speak about, is related to the biostatistics. And it is regarding the introductory portion of the biostatistics. This biostatistics and research methodology is a very important part when we actually enter into our MPC courses. In part 2 also, when we are doing our dissertation, this is an integral part. And understanding of this is an integral part of the whole curriculum of PG. Before I start, I would like just to share one line opinion that this is an important thing in PG level. All the seniors, the authorities who are in the council, CCA, CCRH, everybody, that this research and academics, or better to say, create an awareness workshop type of mentality in the UG level, so that the students, when they come to the PGs, or even they don't come to the PG, they simply go in some other platform, they will have this basic idea of converting their clinical knowledge into research knowledge, and that will ultimately help to create evidences and everything. So, okay, so let us start with the basic introduction. So first of all, this is what I want to share in it. The biostatistics, if I, in a very nutshell, since time is limited, this is many months course in PG, as I told you. So it's not actually possible to sum up if everything and in detail especially. But still, I have tried to make it as short as possible, jot down the points, and for the PG students, especially for your exam, for your later on entrance exams, this I think snapshot version of this PPT might be helpful. So
वाईफाई नंबर
just
और
see just see the contents. This is what I am trying to cover up today. The introduction, the definition, the common statistical terms which we come across when we enter the statistics, the biostatistics, the classification of the statistics which we need for our clinical purpose, the sources and the collection of the data, the presentation of the data, analysis and interpretation of that, and the few basic things which we already faced in a statistics level in +2 level maybe to some extent at least. That is measures of central tendency, measures of locations, measures of dispersion, measures of precision. Then we come to sampling and sampling methods and sampling errors. It is deliberately made red because this is the topic which will be covered by my respected senior, Dr. Shudulin Saha. So I will not speak on that, but this is an important relevant portion of biostatistics as well. And then again, I will end with the last two important portion, that is test of significance and the correlation and the regressions. So let us start. Introduction. The basic things of biostatistics, as we know, the root of the word statistics comes from the Italian word statista, which means the statesman, and the German word statistic, which means the political state. It was for the first time used by Gottfried Achenwald, professor in the Marlborough in 1949, which has been used by him to refer to something, to refer a subject matter as a whole in some context. Now, this in medicine, everything in medicine, whether it's a research or diagnosis or treatment, it depends on counting or measurement. And according to Lord Kelvin, when you measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure, you cannot express it in numbers, your knowledge is of mere and unsatisfactory kind. This is really true. When you are speaking, suppose if you have the numbers, if you have the values, have the percentage with you backing up, then you actually are more confident rather than telling it is better. But if you can say it is better by how much, then your confidence doubles up. So this is a very important statement and it's highlighting the need of biostatistics nowadays. Definition. According to Croxton and Cowden, statistics is defined as a collection, presentation. Each and every word is important. So just think about and try to understand each and every word. Statistics is defined as a collection, presentation, analysis, and interpretation of a numerical data. According to Professor Horace, statistics means an aggregate of facts which is affected to mark extent by multiplicity of causes, numerically expressed, enumerated or estimated according to reasonable standards of accuracy, collected in systemic manner for a predetermined purpose, and placed in relation to each other. So it's a long one, but if you read the definition part by part, I think it's easily comprehensible. It's self-explanatory. You can just go through once, twice, you will understand it. Next, the statistical terms. When you enter into the statistical world, Achha, I just left out one thing, that was statistics, and now we are dealing with biostatistics, not much different. The same statistics which with the methods and the procedures when we apply it in the health science, in the medical field, it becomes biostatistics. So that's the basic, the common linker. It's nothing different. So variable, a term, the first term which we will encounter when we enter statistics are the basic two terms basically, which you can see in one in the slide, variable, the other one will be the next slide, that is data. The variable and data, these are the main two words when we enter into statistics, you get it. So a variable is a characteristic that takes on different values in different persons, places, things. It's basically a particular character on which a set of data is recorded. And data are the values of variables. If I sum up that what is data, what is variable, this one line is enough. Data are the values of the variables. Suppose anything, if you speak about any item, whether it is fruits, when you speak about apples, bananas, then 2 bananas, tree occurs. These are variables as well as with the data. So this is very preliminary, some basic examples which you know. I will just brush up these words quickly. So constant mean quantities that do not vary. For example, pi, which you know we are very much familiar with the values of pi because we need it in our calculations in mathematics in our uh, school levels and even after that. So pi is one such value which is a constant value which we have known to it. And these constant values generally do not require any statistical study. So why we are still considering? Because in biostatistic, mean, standard deviation, standard error, correlation, coefficient, proportion of a particular population, these are considered to be constant for that particular sample or that particular study. So that understanding is required. That what is the constant factor in biostatistics? This is the one. Observation, you know, any event and its measurement is an observation. For example, blood pressure is an event and the value is its measurement. Next, observational unit. The sources that gives observation, for example, object, person. In medical statistics, terms like individual, subjects are more often used. And data, which I told you, a set of values which is recorded on one or more observational units or the factual information collected during research studies. That is data. And remember one basic thing, data, it is actually singular as well as plural. When we talk about many data, it doesn't become datas. It remains data. There is no S to datas. It's a very common thing students initially make. So don't think that there is a word datas. There is no S to data. Data itself is singular and plural in any occasion. Population. It is an entire group of people or study elements, person, things or measurements for which we have an interest at a particular time. So, as you know, suppose now at present the COVID, the pandemic, the entire world population is affected. So now the entire group of people in the whole world is a matter of concern. But initially, suppose when it was in China, so that particular area which started, which was the source of the infection, that was the population which initially was interested about, researchers were interested about. So that population in Wuhan or in China, if I say broadly, was the study of the interest initially. Later, when it became an epidemic and then turned into a pandemic, the whole world population is now a matter of concern. Similarly, sampling unit, each member of a population is a sampling unit, and sample is defined as a part of a population. As I told you, so when you consider the whole population, then a sample is a part of the whole population for which you might think to do a study or you plan something, some intervention or anything. So sample is just like a subset of the whole set. So the subset is sample and the whole big set is population. Now we come to another word, that is parameter. It is a summary value or a constant of a variable that describes the sample, such as mean, standard deviation, standard error, correlation coefficient, etc. So that is parameter. Parametric test, non-parametric test, very important. Parametric tests are those in which population constants such as described, which are suppose means, variances. These are population constant, which I just told you, constants. What are constants in biostatistics? So these are in parametric test. This will be having this will be having I mean a definite example. I mean definite value, and data tends to follow one assumed or established distribution such as normal, binomial, or Poisson. So we'll talk about distribution later on. So in parametric test, always remember the constants will be described. They will have a proper definition and specification, and the data definitely needs to have a normal, binomial, or Poisson. These three types of distribution normally we encounter. And a non-parametric test, so suppose a chi-square is an example of such, in which no constraints of the population is used. Means the data will not follow a specific distribution of critical variables, and there will be no assumption. So whatever conclusion you draw from a parametric test is more valid, but whatever conclusion we come from a non-parametric test is basically not taken to be a valid one. And in fact, that's why we say no assumptions are made in a non-parametric test. Next, classification of statistics. It is just a general classification which we require for normal clinical understanding. Descriptive and inferential. Descriptive means is suppose if you are gathering, suppose an example which I have just written it here, census. Census, the 10 years interval census which is carried in India. What we gather? We gather the name, address, number of family members, few demographic details. This is exactly what is known as descriptive type of statistics. Means it is deals with enumeration, organization, and graphical representation. Representation is also an important aspect of data. Means after you collect the data, it is very important that you represent it also for understanding and for evaluation later on. So representation is also an important thing. So in census, for example, I have given you as an example of descriptive data. It is very important that you just deal with certain descriptive informations as I told you. But now, what is inferential? Inferential is what you when you try to come to a conclusion from those descriptive analysis. For example, it provides the procedures to draw inferences, as I told you, about the conditions that exist in a large set of observations. Example, testing of a suppose you antiviral drug in which the physician will only have a limited number of hypertensive subjects. Suppose if you are testing an antiviral drug on suppose in this situation in COVID situation, then what you actually do, you try to do it in a particular population, particular cluster, rather than doing it in the whole population. For example, vaccine, which is expected to be coming. So initially the trial will be done on a particular few subjects, not on the whole subject. That will be the sample that we can call as a sample. So that inferential, what we are, that is inferential statistics when we try to draw conclusions from those large set of observations. Now, data. This is a very important part of understanding as well as important part of questions also in entrance exams. So, types of data. Initially, it's very broadly classified: qualitative data and quantitative data. In qualitative data, it is nominal and ordinal, and in quantitative, it is discrete and continuous. And in discrete and continuous, we will further have another classification, interval and ratio. So we will talk about all these six terms: nominal, ordinal, interval, ratio, discrete, and continuous. All these six terms is important. So first, we need to know what is qualitative data, as you can understand. So defined as by some characteristics. Suppose if I, as I told you, it's a fruits. So that's the qualitative data. But how much, how many, what are the types of fruits? Those will get some categories. That is why they are also known as categorical variables. But when you stress upon suppose the numbers, then the qualitative variable becomes a quantitative variable. Most of the time in statistics, in research works, actually a qualitative variable turns out to be a quantitative variable when you actually try to draw some conclusion. So again, defined by some characteristic or quality, which is known as categorical variables, and as qualitative variables are very much summarized, I told you, by grouping the observations into categories and counting the numbers in each of them. Quantitative variable, those which are measured on a numerical scale and which is always expressed as numbers, and the differences between the values have numerical meaning. So they are also known as numerical variables. As I told you, the terms. So nominal variable. Nominal variable, I think you better go with this slide. Nominal variable or the nominal data, you can say. There are the categories which are based on the names. There is no underlying order to the names. This is very simple. Suppose in a demographic data, you have males, females. Simply, that is nominal data. You have suppose people with teacher, parent. This kind of classification, school 1, 2, 3, there's 4 different schools names. That much enough is for nominal data, which doesn't also have an order. There is no order also in nominal category or the nominal variables. But in ordinal category, ordinal data category, which is again a qualitative one, doesn't deal with numbers, but it has some order. For example, Likert scale, which is a 7-pointer scale, if you know, which is used to determine, which are used in various research designs. For example, good, medium, bad, or very often improvement of the patients we try to write as mild, moderate, marked, and cured. Suppose the or ideal score I am talking about. Those points or those um, words which I am using, these are actually examples of ordinal variables or ordinal data, where the numbers are not there, but a subjective evaluation, a subjective word is used. That is, suppose mild, moderate, severe. These are ordinal data, but there is an order. There is some ranked relationship, and you can see both of them can be represented in tables and charts. The way of representing data will come to it, so I will not talk about this column now. Just focus on these two columns. So this is nominal data and ordinal data. These are qualitative, and the other two are quantitative, where we will deal with numbers. Suppose this interval data. What is interval data? They are like ordinal data, means they have the classification, they have an order, but those order will be having some numbers. For example, calendar years, temperature, the IQ results. IQ results, we know what is mild IQ, what is poor IQ, what is average, what is good, what is the level of the genius in an IQ. So those words which we used in IQ results also have a value, have a range, this much to this much. IQ is poor, this much to this much. IQ is moderate. So when the ordinal data gets defined with numbers, or better to say numbers which are actually ranges, then it becomes interval. And lastly, ratio. They are like interval data, except that the categories which exist on a scale has a. This is almost similar to interval data. They also have some intervals, as I told you, means ranges. The upper limit, lower limit is there. But the additional part of ratio is they also have an absolute 0 point, which is not there in the interval data. There has to be a 0 point. Somewhere there may be a zero. For example, speed. As you know, the lowest limit of speed may be zero. Height, weight, salary, word count. So these are the things which always have a true zero. And in interval data, it may not be. It may not have a zero somewhere. But the ratio data, they has to have a zero at some point of time as a lower limit. Okay. So these are the examples of some nominal data, nominal variables, nominal scales, you can say also, where there is no inherent order, as I told you. For example, types of disease. When you say cancer, different types of cancer, COPDs, these are the names, just as it is gender, male, female, socioeconomic scale, rich or poor. Simply you just give the terms without any exact evaluation of what are the criteria to become rich, what are the criteria to be poor. So it will simply have the words rather than having any quantitative definition. Okay, ordinal scales. As I told you, they will have an order. You can see from the diagram, hot, hotter, hottest. So this is having some order. This is a superlative order. Next, severity of disease, as I told you, mild, moderate, severe. Socioeconomic scales, upper, middle, low. These are all orders. And ordinal scale is that. Interval scale, as I told you, there is no absolute 0 point, and ratio scale, there will be a 0 point. So in temperature, if it is centigrade and Fahrenheit, it will be interval scale. But if you talk about Kelvin scale, in MCQ, be careful. If it is talking about the Kelvin scale, then it will come into the ratio scale. It will be a ratio type of data or a ratio variable, not interval. So be careful. Now, to sum up this data or variables or scales, if I say in one word, the nominal type of data, when you gather data, the nominal type of data is very much the weakest form, you can say. They only have attributes, and they have attributes which are known by only names. Ordinal data attributes are ordered, a little better one, which is often can be used in certain um, qualitative testing, like in chi-square testing. Other tests are also there, which I will come to the last slides. Interval distance is meaningful, means that distance or that gap, which the range which I was talking about, that is meaningful. And ratio, they have an absolute zero. These are the main points from each of them in a nutshell. Okay, now the next part, the sources and the collection of the data. Here, data is obtained by investigator himself. This is the first-hand information. Understandable. The data already recorded is utilized to serve the purpose of the object of the study. Simply when you are recording it from the OPDs or IPD register, that is secondary. And if you are directly getting it from the patient or from the investigator, then it is primary. The main sources of collection of data in medical statistics, generally, definitely experiments, uh, which may be clinical, which may be in vitro, in vivo, surveys, which we do very often, and the records, as I told you, from the registered records. Experiments and surveys are to generate data needed for specific purpose. Whenever you do an experiment, means a trial, or you do a survey, there is always a something in mind. That is why you are going for it. And the records, suppose you are trying to elicit something from the records, which has been already a ready-made data. It's something like retrospective study. You cannot change anything. Suppose you are trying to evaluate the prescriptions in a doctor's clinic. Suppose last 1 year, the prescriptions, which one, the types of patient you have seen, you want to set some analysis out of it. You try to make some retrospective outcome of those 1 year patients in a doctor's chamber. Then you actually are going with the records and trying to get some analysis out of it. So that analysis will again depend upon what type of data you had in the prescription, what the hypothesis you may frame out of it, then what will be the choice of your testing significance, and then you ultimately try to go for some evaluation, I mean comparison. I will come to it one minute. So methods of collection of data. The method of direct observation. Clinical signs and symptoms and prognosis are collected by direct observation. Vital statistics and morbidity statistics are usually collected by visiting house to house. These are the different formats which we generally encounter. There may be many things beyond this, but these are the basic things. If you are in a research-oriented platform, you understand that these are the way how you get the data. This method is followed in a community where literacy status of the people is very high, and prepared postage stamp is to be attached with a questionnaire if you are going with a mailed questionnaire format. Next, the presentation of data. This is a very big chapter in the biostatistics and a very easy one, but it is important because every data cannot be presented in the same format. As per the type of the data, which we already talked about, nominal, ordinal, ratio, interval, quantitative, qualitative, you need to tabulate them. I mean, you need to present them either through tabulations or charts and diagrams. So one thing I forgot to tell you, that is the data which was in the slides, that was it may be nominal, it may be ordinal, it may be ratio, or it may be interval, but there are certain another very basic things which I missed out in the slide. Sorry for that, but you can just note it down that data or variables may be independent variable, may be dependent variable. Very basic thing which I haven't put in the slide, but you should know that what is independent variable and what is dependent variable. Independent variables are those which can be manipulated by the researcher and to create an effect on the dependent variable. And dependent variable, as you can understand, it's an outcome or response which is due to the effect of the independent variable, which the researcher wants to predict, to explain. The simplest example I can give you, for example, you know about arsenic album, what we are doing it with that for the last 6 months. So suppose if I say arsenic album as preventive for COVID-19, if I use this statement, then in this statement you have the dependent variable, you have the independent variable. So what is the independent variable? The independent variable is arsenic album 30, the dose, the medicine of which is in your hand, in the hand of the researcher. And what is the dependent variable? The prevalence, the occurrence of COVID-19, because you are using arsenic album to see whether how much preventive it is or not. So what will be your dependent variable? After arsenic album, how much COVID-19 is created or not? So your dependent variable COVID-19 is totally related with your independent variable, that is arsenic album factor. So this is the best example I can say of at present, obviously, in this pandemic situation. So dependent variable and independent variable. And there is one more variables, that is confounding variables. Confounding variables or extraneous variables, you can say, which is not a part of the study initially, or maybe not a part of the study upfront. You may not see it, but it will affect the measurement of the study variables. For example, if you are going with assessment of certain drug in a clinical, suppose you take an example if you want to see the effectivity of certain drugs like Spongia mix in cough, especially in dry cough situation, and you are trying to enroll cases, and at the same time you are assessing the patient by using some cuff parameter or cuff scales you are using, no problem. But in doing that, if you are not taking the smoking of the patient into account, that may be an issue. Why? Because it might happen when the patient started the medicine, he or she might stop smoking as well. Now, that smoking factor will be an extraneous variable, or he may be continuously smoking. Either way, either he or she stopped it, or he or she continued it. So that smoking factor will be affecting your outcome of the study. Will be affecting the response of the patient, and in that way, it will be affecting the result as well. So this kind of, suppose in this what I said, smoking is one of the extraneous variable which was not into the account, because your main variable was the drug which you want to see, and your dependent variable was definitely dry cough. So in this way, certain factors always remains in a study which are extraneous variables or confounding variables, and which needs to be looked for. Otherwise, there will be biasness in the outcome, in the result, and which needs to be tackled as well in the research design, in the study design. Okay, so this I missed out in the slides, which I told you. Coming back again to the slides. So presentation of the data. To sort and classify data into groups or classification. You can understand, simple. So presentation means you need to sort what you have got. Means you have a lot of data in your hand, raw data is in your hand, you need to classify them, you need to group them. What is the basic objective? To make data simple, concise, meaningful, interesting, helpful for further analysis. And what are the two methods? Tabulations and charts and diagrams. So let us see the different criteria of tabulations. Tabulations is not just drawing tables in childhood. Nowadays, nowadays you need to, when you are tabulating a data or you are presenting a data in a table form, you need to have these things in mind. So what are the things? Devices for presenting data simply from the masses of statistical data. Yeah, you're doing that. It should be precise, it should be understandable, and it should be self-explanatory. You are looking at a table and you need somebody else to explain it, then it's not a proper presentation of the table, probably. Every table should have a title, and that is placed at the top of the table. The title must describe the content clearly and precisely. Items should be arranged alphabetically or according to size, importance, or causal relationship to facilitate comparison. Rows and columns to be compared with one another should be brought together. The unit of measurement must be clearly stated. Percentage can be given in parentheses. Total can be placed at the bottom of the columns. Reference symbols can be directly placed beneath the table for any self-explanatory notes. 2 or 3 small tables is preferable. If you don't want to sum up everything in a larger one, break it up into 2 or 3 tables. A table can be simple or complex depending upon the number or the measurement of a single set or multiple set of items, and is of 4 types. For example, a frequency distribution table. Table is the first split into convenient groups and the number of items which occur in each group, and is shown in the adjacent columns. You just see the figure. This is an example of a frequency distribution table. This is class interval. So this is the class boundary. We need to make the classes uniform. So the upper limit and the lower limit, they becomes uniform with the next order. Next interval, sorry. And class mark is the average or the midpoint of the class boundary. And this is the frequencies. Suppose this may be the marks of the students of class 8 in the final semester, and it has been categorized that 8 students might have received marks between 70 to 74, like that. That's roughly I'm saying. So this is the total which will be presented, and this is a classical example of a frequency distribution table. The next one is the contingency table. Tables that report the frequency distribution of two nominal variables. Again, nominal variables, which will be just having names simultaneously and then include the totals. So let us see the example of contingency table. So this is contingency table. You can see these are the names of the attributes. These are rows, chips and dips and cookies, and related with book. These are the things. These are the activities, and they have given some values. So as I told you, every qualitative data ultimately lands up to become a quantitative data. This is how, because these are the attributes which are totally qualitative. But when you put numbers, ultimately they get converted into have a numerical value. But contingency table will actually be focusing on this attributes, the two nominal types of variables. Definitely they will have some numerical value. So this is a combination of a nominal getting converted into a quantitative variable. And the last variety is multiple response table. When the classification of the cases is done into categories, simply categories are there which are neither exclusive nor exhaustive. For example, the last table, the types of the group, frequency, percent. So it is nothing correlated. You simply write the groups, you simply write the frequency and the percentage. But it's neither exhaustive and nor exclusive, as I told you. And miscellaneous tables, these tables are used to present data other than frequency or percentage distribution, such as mean, median, mode, range, and SD. So if you see, when actually this becomes more, this is going theoretical, but it becomes more practical when you actually go through certain research articles. You go through the trials, published articles especially, and in the published article, when they give you the statistical analysis part, the data analysis part, in that you just go through. You will see the presentation of the data, how they're presented in the table you go through. So take up, read the research papers, go through the journals, then you will actually understand that what is the what was the type of the data, what was the presentation format in the table, what type of table is that out of this four categories which I'm talking about. So more you actually go through the research papers and the material which is there written in that paper, you actually get a practical idea about what I'm speaking. Biostatistics actually is all about that only, because the things which we speak in biostatistics mostly is done by the software. I mean, a biostatistics software like SPSS or Microsoft Excel. Microsoft Excel also have a lot of statistical like activity, and then SAS. This is another important Minitab. These are different softwares which you use to evaluate certain biostatistical parameters. Actually, need not to do. Suppose when you talk about mean, median, mode, or is standard deviation, or even the values of p values coming from chi-square test or a T test or unfair T test, you need not to do anything. You just place the data, the values in these softwares, they will give you the answer. So why then we actually study biostatistics in detail? The why is basically you need to have an understanding. Because when you go for a trial, you should know what you are dealing in the trial. You are dealing with the data and what are the types of the data, what you can do with this type of data, what I can say as data analysis. Before going into the data analysis, you should have an idea about the data. Then you can actually get these things. I mean, then you can actually make a proper research design. Then you can actually properly go with the trial. Okay, so this is the tabular form of presentation. And beyond the tabular form of presentation, it can be represented by different charts and diagrams as also. For example, in the quantitative variables, you can use these other forms, histogram. I'm coming to it one by one. The frequency polygon curve, the ogive, the line diagram, the scatter plot, box and whisker plot is a new one. You often might getting the MCQs is a trending question as well nowadays. Qualitative variables, these things are also new to you. Bar chart, pie chart, pictogram, spot maps, Venn diagrams is also there in mathematics in plus 2 levels. Okay, so starting with histogram. Histogram, as I told you, you can already see in the previous slide, it is for the quantitative variables. So quantitative variables and histograms, as you can see, it is basically a column, rectangular columns, and it's for use for a continuous scale. Achha, I think continuous scale, continuous data and discrete data, that thing I also messed up. What is this continuous data and what is this discrete data? Continuous data is something which will be having, I mean, if I say discrete, that will be better. Discrete is actually something which will be having a, which will always be represented in a whole number. And continuous data or continuous variable is something which may also have a range including the fractional values. So remembering that way, that is the easiest way. Discrete values is actually when you have always whole numbers, and continuous is actually which also includes the fractional numbers. And there are certain parameters which is often confused in both the categories, whether it is continuous or whether it is discrete. For example, I think the most examples coming to my mind is age and blood pressure. Age and blood pressure, these are often treated as discrete variables, but strictly speaking, they are actually continuous. So remember this one thing, discrete are dealing with whole numbers, continuous are dealing with fractional numbers as well. So now this histogram, as I am telling you, it is actually dealing with quantitative variables, and most of the time it is dealing with continuous numbers. It's continuous variables. And in histogram, there will be no gaps in between, no gaps between the columns. Okay, so you can depict any, suppose height of an individual. It's not, though the scale is not that, but still suppose the height of an individual, you can simply depict on a histogram. Okay, next is histogram frequency polygon. Why I am given it like this? Because if you see it is histogram only, but you are seeing a line which is joined by the points, and the points are placed in the middle of the columns. The points are placed in the middle of each and every column of the histogram of the bar. So the line which is obtained, just listen carefully, the line which is obtained by joining the midpoints of each and every column in the histogram is actually known as frequency polygon. So frequency polygon is nothing new. It is just a line which will be obtained by joining the midpoints of the bars in the histogram. Easy. Next, this is only frequency polygon which looks like without the histogram, which is histogram bars. Next is frequency curve. Next is frequency curve. So frequency curve, it is obtained in the same fashion, but this cumulative frequency curve, which is have a different name, that is known as ogive. For ogive, we generally use the cumulative frequency. Cumulative frequency means your frequency keeps on adding up. Your frequency polygon is also a type of frequency polygon, you can say. But in ogive, what happens? You plot the curve as per the cumulative frequency. Your cumulative frequency means each and every. Suppose one group having now frequency having 4, another group having 6, another group having 4, 6, suppose 2. So what happens? The cumulative frequency will be like this. First it will be 4, then it will be 10. Next it will be keeping on adding up. Next it will be 12. So only on frequency, if you plot, then it's a normal frequency polygon, a normal frequency curve. But if you are plotting on frequency, cumulative frequency, then it becomes a ogive, which you can see. It looks like this. And what is the main use of this ogive? Basically, then why we actually require this ogive? We actually require this ogive to decline the cutoff. We mean, suppose the cutoff, anyway, it may be the cutoff marks in MD entrance exam or in any exam or anywhere. So cutoff, and it also helps to give you a direct idea of the mean and the mode, median and the mode from the graph itself. This is a line chart or graph. The line chart of the graph, this is actually, okay. Yeah, the line chart of the graph, it's simply plotting the values in the x and y axis and then getting the line. It may be a linear line, it may be a non-linear line. So in all these three lines are basically non-linear, they don't have any linear relationship. Maybe just because it's a stock marketing example, maybe that because of that. So it's not necessary that it always has to be have some proper correlation or regression. It may be this happens at a non-linear as it's shown in the figure. Okay, scatter or dot or a correlation diagrams. Scatter or dot or correlation diagram. This is interesting because till now, which we are dealing with, we are all dealing with one type of variables, just one type of variables. Whether I told you whether it was the height or whether it was the marks, just one type of variable. But suppose if you want to see the correlation, if you want to see the correlation between two sets of variables, then you have to go for this. You have to go for this. Suppose if you want to see the correlation of the weight, suppose during a development period, suppose you want to see the correlation of many child in a particular community. You plot the weight here, you plot the height here, and you try to correlate the when height is increasing, weight is increasing or not for that particular community, or not only increasing or whether it is showing a proper correlation or not, whether the correlation is very low. Correlation I will be discussing in the end. But suppose there has to be two slides, two variables, height and weight, and you try to correlate whether they have a positive correlation or a negative or they have no correlation at all. So this is basically to understand the correlation between two variables. We use scatter or dot diagrams. Box and whisker, as I told you, this is a unique presentation of quantitative data using the quartiles. So what are quartiles? Quartiles, I'm going to that slide so that you can have an explanation. Quartiles is a discussion here. Quartiles is measures of location. This is an important topic as well, which will come to it. So I already came now. So quartiles here, you find it quartiles. So what is quartiles? Quartiles, quintiles, octiles, percentiles. Probably you are more familiar with the word percentile. Quartile is also such. Percentile means when you distribute the whole set of data into 100 parts. Oh, sorry, 99 parts. You just see this diagram, I think it will be okay. This is quartile. Suppose you have this whole set of data, 100 data you have, and you divide that data into four parts. So the first part 0 to 25 will be quartile 1. The second part will be 25 to 50 will be quartile 2, then quartile 3. So dividing into four parts and having three quartiles. Similarly, if you divide that into deciles, if you divide in deciles, you will having total 10 10 deciles, but it will have 9 parts. Similarly for percentiles also. So this is giving you an idea of the locations. So as I told you in the OGIV also, it helps you to understand the location of the quartiles, understand the location of the median. So this is to understand the location of that particular variable. So the quartiles is as such, which the whole data can be broken into four parts, and it may be Q1, 2, or 3. So that quartile, which I just talked about, coming back to the box and whiskers. So now it will be, I think, understandable for you. The whisker, this you just follow the lines. This whisker shows the lowest value. You have a data set. The lowest value is represented by this line. This line will show you the lower quartile, which is maybe the Q1. This line shows the median. This shows the upper quartile, Q3. This shows the highest value, and this shows the interquartile range. And this is the scaling parameter based on which you are marking this box and whisker. This box and this whisker, you are marking it. So one thing you have to remember about this box and whisker, that this is a quantitative data presentation, definitely using the quartiles. Okay. Next is bar diagrams. Now these are things for qualitative presentation, where you may or may not have a quantitative issue. So qualitatively, if you want to present something, you want to show something by this is by changing colors, by changing length and widths. Automatically, you can do it by doing with bar graphs. You can see the different colors depict something different. The different colors as well as the length of the colors also depict something. So this is qualitative understanding. Pie diagram as well. This also has been this drawing a pie requires a quantitative calculation definitely, but the 360-degree angle of the circle is broken up into different angles as per the values of. For example, you can see in this it is given how many people are using Facebook or Quote, in social media, different apps are given, and each and every color um, represents the number of users. For example, it is easily understandable from this pie diagram that this blue color is the maximum user-friendly app, and after that, definitely your orange is coming. So like that, from the visualization, you can conclude something. So this is basically for qualitative variable presentations. This is pictograph presentation. Pictograph presentation means you can understand that this is pear, this is watermelon, this is orange, this is apple and banana. But number of children who used it, rather than drawing children, they have drawn a diagram of the pear for the particular fruit itself. So you can easily understand that the 7 people are using pear, but other are consuming just one. Each children is consuming the other fruits. So this is pictograph, very easy to understand from a glance. And if they always remember, though it is pictograph, though it is qualitative variable presentation, but they have a quantity or a numerical information in the background from where they are either drawn or where they may be depicting. So, as I told you, this quantitative and qualitative, they are very much intermixed or interrelated. Venn diagrams, this is also very important things, part of the arithmetic in class 2 levels, which is basically done by circles. You can represent any kind of figure. You can do it with squares, you can do it with rectangles, but circles is the more important diagrams which is seen in the mathematics books. What is the meaning of it? Suppose if I take this I think it will be easily to understandable because this is two variables. Suppose A is one variable, B is another variable. So what is A? Suppose what to take an example. The meaning I am telling you, for example, A, this is this part which I'm just highlighting, this part is exclusive for A, and this part exclusive for B, and this part, the intersecting part, is a common part, but which is commonly present in A also, commonly present in B also. Suppose A is a student who is taking who has the subjects in his graduation level that is honor. Suppose this I think an example good one. Two students in a college who have taken up BSc for BSc. One has gone with physics honors, and another one has gone with chemistry honors. So, what will be the common part? The common part will be the past subjects. Means they might have to study English, might have to study Bengali, might have to study zoology, mathematics, which are environmental, etc., which are the common part. But what is exclusively for A, the physics in which he has taken honors, or B, chemistry for which he has taken honors. So like this, you represent this Venn diagrams. stem and leaf design. This is again an interesting one, very new method nowadays utilized and important for MCQ as well. Suppose this is actually representing numbers of a student. Suppose in a pathology exam, 200 was the full marks, and this is the numbers which has been depicted in this stem and leaf design. I'm telling you, probably you may be thinking, where are the numbers of the student? It's like this. Suppose the full marks is 200 and students have obtained marks mainly between 90 and 110. Okay, and this 6, 7, 8, these are the 10th values, means this is depicting 60, this is depicting 70, and you have to just add the number which is written here. For example, you take this 8. 8 means one student have got 85, next student got 83, another student have got 86. It's like that. It is plotted like this. And from this, what is the utility of this pattern? Utility of this pattern, from this you can easily understand that what is the maximum cluster of marks in the class or in the pathology paper. So you can easily say that it is between 90 and 110 because you can say maximum marks are jotted down between this area. Or if I say what is the maximum, obviously between 100 and 110 because this 10 depicts 107, 101, 100, 101 again, 105, 104. So like this is the range which has the maximum number of students. And what is the highest marks? You can say 141. What is the lowest? 68. There's two students in the 70 category, 75 and 78. So like this, stem and leaf design, which is very easy to understand, and in one glance, you can really go for it. And remember, this is always for discrete data because these are whole numbers. You can understand it. Okay, what is this? The last, another pictorial presentation, and this is known as spot diagram. So you can easily understand from the whole world map the difference of the red color in the whole world map, that there is a difference in each and every country presentation. This is what we call as spot diagram. You can see the red, that means the proper red is for the countries with 100 or more confirmed cases. You might be surprised that only 100. This was actually a whole picture in the month of March, April. That's why it is only 100. And the rest of the red colors you can see is very faint. Suppose if you see in the many parts of Africa, even in Australia, where it is very fainted. But you see USA, Canada, you see obviously China and then India and this part of Russia also, where it's more red, and that redness depicts that it is more than 100 for confirmed cases of COVID. So this is how you represent a spot diagram. The variable, the quality you will use is dependent upon you. For example, they have used the variation in color. You might use something creative, more creative other than this also. Okay, so these are the different graphical presentation. Next we come to the measures of the central tendency. In measures of central tendency, we have three main things, which is mean, median, and mode. And very easily it can be done. Mean is actually the sum of all the values by total number of values. Median is the middle value, but middle value, not only a middle value, it has to be a middle value when the data is arranged, either ascending or in a descending order. For example, if in the figure you see, you can see the height is decreasing, means it's a descending pattern of arrangement of the people. And in that arrangement, means after that arrangement, either this pattern or the ascending pattern, you go for the middle value. But when your n, means the total number, is odd, then you can get a middle value. But if it is your, suppose it is 13, if I think you just calculate, and this is I think 14. But when it is even number, then you don't get a middle value. Then what you do? Then you go for the n when it is even. You go for the middle and the next two values. You consider the two middle values and make an average of the both. So this is when n is odd. This is when n is even. When n is odd, directly you suppose this is 13. I think 1, 2, 3, 4, 5, 6, 7th value is the middle value. because the formula is like this. When it is n is odd, then you do it like this: n plus 1 by 2 means 13 plus 1, 14 by 2 is 7. So the seventh position is the median value, straight from the diagram. But if it is 14, then you have to go like this: n by 2 plus n plus 1 by 2, and the whole thing by 2. So it's like this if it is even. You have everything in the text, you just recapitulating. And mode, which is the most common one. Let us take this example, I think it will be more clear. So this is a 3 set of data. Maybe in a tuition class, out of 20, these were the 7 students who actually got the marks. So you know what is the maximum marks, what is the minimum marks, what is the most obtained marks. Most obtained marks means, as I told you, the number of frequency which will be repeating mode maximum. So in mode, what is the mode? You can see 7 has been received by 2 students. That is mode 7. Median, you go for the middle, first arrange it and see. Since there are 7 students, so 7 plus 1, 8 by 2 is 4. So the fourth number will be the median. It is here. Mean is very understandable. Mean is the total numbers by n. When you add all the numbers and by the number of students. So n is 7, you just add up and you see what will be the value. Range, as I told you, maximum minus minimum. Upper limit by lower limit. So it's 14 minus 5, 9. So this is the how you go for the measurement of central tendency. For PG purposes, I think this thing additionally you have to know that A and B are positive numbers. Suppose you have to go beyond the arithmetic mean also. You need to know what is the geometric mean and what is the harmonic mean. So if it is arithmetic mean simply, which we saw now, and I'm doing just taking examples of 2 numbers, A and B by 2. That is enough. When I mean sum of the 2 numbers. But if it is a geometric mean, then it will be the square root of the numbers. Suppose if it is 4 5 numbers, then it will be like that only: A into B into C and then the whole square root. If it is a harmonic mean, it's just reciprocal actually. It's a reciprocal of the means. So it is given like this: A by B by 2, and obviously by reciprocal of that, it will be 2 and A by B is A plus B will be downstairs and AB will be upstairs. It's reciprocal. So in other words, if you formulate, you can say harmonic mean is geometric mean squared by arithmetic mean. This correlation is important. You may need to do little calculations. Okay. Measure of locations, as I told you. So median already you can understand it's a measure of central tendency, as well as it comes under the level of measurement of locations. So median is clear, and quartiles, quintiles, octiles, percentiles. So basically they have all the same theme, means breaking up into 4 parts, breaking up into 100 parts, like 10 parts, 8 parts, and 100 parts. Like that, the names are differing: quartiles, deciles, and percentiles. 4 parts, 10 parts, and 100 parts. So these are the measurements of locations. Now, measures of dispersion or variation. Range already is known to you, which I have just shown. Range is very easy. It's the simplest difference between the highest and the lowest figures. For example, at diastolic blood pressure, as you can see, the range will be in this data is 71 to 95, or by actual difference, we have a total difference of 24. It's the simplest one. What is the demerit? It is not much of practical importance. Indicates nothing about the dispersion of values, and it's between 2 extreme values. So nothing much than that. What is important next is the mean deviation and the standard deviation. So I think it's better go with an example. This chart will help you to explain. Suppose these are 15 students again, and you have the marks obtained by the different students, and this is the deviation from the mean. Now, what is mean? Mean, as I told you, you simply do the total and total by the number of the students. So the total was 765, number of students is 15, and accordingly the mean becomes 51. So your mean deviation is, again, see, your mean deviation is average of the deviation from the arithmetic mean. So in every student's marks, you have to make the deviation, count the deviation. If your mean is 51, so it will be 51 minus, sorry, it will be yeah, 51 minus your marks which you have obtained. So 51 means how much the student have obtained is away from the mean marks. That is actually the idea. So that is 51 minus 35, 16 away from the average mean marks. So 40 means 50, 11 away. So like that. So it like that, make this chart. Suppose it may be negative, it's 51 is a mean. So 55, that means he's plus 4 ahead, plus means he's ahead, so it's minus 4. So in that way, you tabulate this mean deviation, means how much the marks are away from the mean. And then you do the square of this mean deviation. The square of the mean deviation, you write it down, and then you get a total of the square of the mean deviation, and total of the square of the mean deviation by n minus 1 give you variance. Okay, variance is another term you need to know. You need to know the mean deviation. This is the one. You know, need to mean deviation squared is the next column. After that, variance. Variance is obtained by the summation of the mean deviation square by total number minus 1. Total number minus 1 because total number is again odd. So it will be odd, 15 minus 1, 14. So what you get as the result is the variance. And when you square root this variance, then you get your standard deviation. So standard deviation is the value is not given here of standard deviation. But if you just do the square root of this 596.14, you get what is the standard deviation for this particular sample of data. So now we come to the definition. So what is standard deviation? Is most frequently used root mean square deviation. So it is, this is the square deviation, mean square deviation. So mean, it has to be square root of this mean square deviation. Square root of mean square deviation by the total number of frequencies, total number of candidates. So if the sample size is less than 30, as you saw here, that's why you use it in the denominator n minus 1. Otherwise, you only go for n, means what the n is actually. And SD gives us the idea about the spread of the dispersion. What is the utility of the standard deviation? It's actually give you the idea. Means you have 15 different types of marks. By understanding the SD, you will actually understand that how much the marks is spread out, how much is the spread out of the numbers. The larger the standard deviation, greater is the dispersion of the values about the mean. It's understandable. If you get a greater value of standard deviation, that means your values are much away from the mean. So, which means there's a lot of, the range is huge, you can say in other words. So, this is standard deviation. Next, we come to the measures of precision. The measures of precision is done by two things, that is coefficient of variation and standard error. Coefficient of variation of a data series denotes the standard deviation expressed as a percentage of the mean. You can see the formula. This is the formula, coefficient of variation. This is the sign of the standard variation, and this is your mean. So simply SD by mean is your standard deviation. I can see here the sample mean is total by the number n. This is a standard deviation, square root of the mean deviation square by n minus 1, the whole root. That is your SD. So this is your SD, this is your mean, and SD by mean gives you the coefficient of variation. It actually denotes the relative size of the standard deviation with respect to the mean. And clinically, what you need to understand, it can be conveniently used to compare variability between the studies. So as I told you, suppose you have taken up a study and you are comparing with another group. So what are the basis of comparison? You may say that I want to see the efficacy of the medicine in this group and that group also, but there has to be some parameters on which you will compare. So coefficient of variation may be one such parameter based on which you can compare. Now you have to set your data in such a way that you get the mean, the standard deviations, and then the CVs. So coefficient of variation is a very used, one of the very used uh, comparable parameter in the studies to compare things. So it has some good utility. So as I told you, just go through the research papers. Again, you will find that they will say the mean for group one is this, the mean for group one was that, the standard SD for group one is this, the SD for group two was this, and coefficient of variation was this, and for the group two was this. So that group one, then group two maybe the group one was the group before the treatment, the group two maybe after the treatment. So in that way, you can summarize your own simple basic clinical data from the patients you are seeing into a statistical mode. And when you talk in this mode, then it becomes more acceptable in the science background. Now, this is what you see the standard error. This is another one. Coefficient of variation is one other measure of precision, and the next one is standard error. So standard error we always have to count when you enter into a trial. So standard deviation, what is the formula? Standard deviation by the number of samples, but the root of the number of the samples. Okay, so standard error is very, very important because standard error of mean is much smaller numerical value than SD and is often represented in place of SD. Suppose you are not using the SD as a coefficient parameter, sorry, as a parameter for comparison, you might use standard error. However, this is an erroneous since standard deviation is meant to provide an estimate of a population parameter from a sample statistics in terms of confidence interval. Now, for taking standard error into account, you have to know many things like what is the normal distribution, what is confidence interval. These things you have to know. So I will just discuss it after this. But next slide is important. We use standard error to define a range in which the true population value is likely to lie. Means suppose you have taken a sample or a population for study and there will be a range, means where you expect your data to be falling. Suppose you have taken a population where they have mostly taken arsenic and you expect that that cluster means most of the time will be falling in that particular range, means that area, the population which you have taken, most of the people who have arsenic, suppose you take it like this, arsenic, they have taken arsenic, for some have taken for 3 days, some have taken for 7 days, some have taken for 5 days. Suppose this is the variation you get when you talk about in a community regarding the prevention of arsenic they have taken regarding COVID. So now if you want to draw some evaluation, you will go with a study setup definitely. So what happens? You may, you know that the Ayush advisory is basically OD into 3. It was basically OD into 3. And most of the people definitely have taken in that fashion, but there are many who are advised by many other doctors in private or others who have taken OD into 5, OD into 7. So you take everybody into count. But when you actually draw the data or represent the data, you expect what? OD into 3 should be your maximum response from that particular sample. And your confidence interval means your most of the data will be lying within that OD into 3 category. Okay, so in a very roughly I am trying to explain is better I go with some diagrams, it will be better. I think this diagram will be this is actually better explained when you go with the frequency distribution. So frequency distribution, suppose this is the normal curve. This is the normal curve of the frequency distribution, and suppose as I told you, your maximum data will be maximum data means what do you expect the patients to be taking OD into 3 will be falling in between this in between this in between this see this diagram 95% will include standard deviation. This is taken to be standard, means if you just follow this cursor, this is the area, this is the area, this much This is the area where you expect your maximum data to be present. There may be few flying data like OT into 5, OT into 7, OT into 6, which may be outside lying here or here in the two tail. But your maximum data OT into 3 may be lying here. So this is what is represented in form of a normal distribution. And when we talk about here, again coming back. So, yeah. So this is the confidence interval, means that will be the interval which will be taking into account. That is taken as to be having a 95% confidence level, means 95% of your data is only present in that particular part of the normal distribution. That what we mean by 95% confidence interval. And from the, if I read this line, it will be more clear. From the properties of the normal distribution curve, it can be shown that 95% of confidence level of the mean would cover having an error of 1.96 errors on either side of the sample mean, and having 95% probability. That is, I am telling, that has a 95% probability of including the population mean. Means 95% of the data will be in that particular part of the distribution. If it is 99% of confidence interval you want to take, then you have to increase the area a little bit more in the tails also. But for that, you have to optimize the error. The standard error should be increasing to 2.58. So 95% confidence interval is the most widely accepted in the trials with 1.96 standard error. This is a widely accepted parameter we go in the trials with. So in short, more the confidence interval would be narrower, smaller will be the standard error of mean. So a sample, if it is larger, standard error of mean would be smaller, and the confidence interval would be correspondingly narrower. So this is the gist of the whole thing I'm trying to explain. It is always to take better to take a larger sample, and standard error of mean will always be smaller in that case, and your confidence interval will also be correspondingly get narrower. Now, so frequency distribution, which I already came to, it is useful to summarize a set of observations with frequency distribution. The summary may be in form of a table or a graph. The majority of the distribution that quantitative technical data follow a unimodal, means the data have a single peak, which you just saw, with a tail on either side. However, they are skewed. Skewedness is something which may not. Skewedness means we don't have a normal distribution at that time, which is substantially longer tail on one side. It may be on the left or maybe on the right. I'm just coming to it. So this is skewedness when you don't have a normal distribution like this. Normal distribution criteria, you can clearly understand that it is having a bell-shaped structure. Bell-shaped symmetrical, bilaterally symmetrical curve. The two ends will never be meeting the baseline. Just the two ends should never meet the baseline. Median mode, and what is the main criteria? The mean median mode of a distribution of a normal distribution should always coincide at 0. And the variation and standard deviation for such distribution should always be 1. So if it is not so, but if it is like this, then we call it as skewedness, which have a deviation from the normal shape and structure. In some cases, the data is not showing a normal distribution, as you can see. In that sense, it does not mean to have the mean coinciding with the median and the mode. When your mean and mode doesn't coincide, so in a right-sided skewedness, you can see in this diagram, the mean is more than the median, and median is more than the mode, as you can see in the diagram. And thus the opposite in case of left skewedness, where mode is more than the median and median is more than the mean. This is understandable and it's factual. You just need to see which type of distribution you are getting after getting plotting the data. So this is the criteria. Suppose this is an example where you have a distribution of the monthly temperature in Durham, and it has been seen to have a normal distribution. You can see these are the temperatures they are plotting, and it seems to have a bell-shaped distribution, which is having the characteristics of a normal distribution. but not necessary it has to be always. For example, this is another weather parameter, maximum wind speed for two consecutive convective periods in the month of May. You can see it is having a left-sided skewedness. Left-sided skewedness means wind speed is mainly fluctuating between this 15 and this for 39. I mean, sorry, 20 to 19 to 39 is basically mainly fluctuating. So 24 to 39, and the rest you can see is dropping. So it's not having a normal distribution. Okay, another important thing, another associated factor with this normal distribution is the Z-score. Calculation of Z-score is a measure of the location of the variable, and the result is in terms of SD away from the mean. Again, the idea is the same. To find the location of that particular variable, your data has so many variables. So your variable, how much away it is from the mean or from the SD, you need to know that. If the value of the Z-score is more than 2, it implies that the value is lying more than 2 SDs away from the mean. Generally, this is the formula. This is the individual score for the particular variable, and the mean you have and the SD you have, and you calculate the Z score. So Z score will be like this. If it is having, since the standard deviation 2 is taken to be standard, as I just told you, 1.96, which is equal to 2. So 95% confidence interval with 2 standard deviation is taken to be as a standard parameter. So in that context, every time your standard deviation becomes 2, and if your Z value according to is falling within -2 to +2, then you can say it's a normal ordinary value of Z. But if it is having a score less than -2 or more than +2, then it is unusual values of Z. In that cases, we can confirm that the variables is much away from the mean, much away from the SD. This is the interpretation. Okay, almost end part of this presentation, that is hypothesis testing. One of the major application of the biostatistics is hypothesis testing. Much of the research begins with a research question that can be framed as a hypothesis. This whole thing which we have now just seen, just a minute. The whole thing, so far we have studied the different forms of data, the presentations, the measure of mean, median, mode, means the central tendencies, the dispersion. All these are actually used in what? Used in framing a hypothesis testing. And much of the research begins nowadays with a research question, and that can be framed as hypothesis. The statistical convention which we nowadays use in all the trials almost is to begin with a null hypothesis, where it will say that there is no difference between the two groups, like that they will say. And the alternate hypothesis will be saying no, there is a significant difference, and we have to prove it whether really the null hypothesis is right or the alternate hypothesis is right. So in this way, suppose we take this an example, we need to see the effect of biofertilizer X on plant growth. So your null hypothesis will say application of biofertilizer X do not increase the plant growth. See, you are giving fertilizer doesn't affect, and you are not giving a control group where it's also having the same result. So is it this or is it this? Means application of biofertilizer X increase the plant growth. Okay, just one thing here. This hypothesis may be one-tailed or two-tailed. Means if you have written the line like this, application of biofertilizer X alters the plant growth or changes the plant growth. That is also an alternate hypothesis, but you are not telling whether the change will decrease or change will increase. So if you just have written alter, then it would have been one-tailed hypothesis. But if you have indicated the direction of the change, it will increase, or suppose it will decrease, then it will be a two-tailed hypothesis. Okay, so just a little addition to this one-tailed hypothesis and two-tailed hypothesis. But this is in a nutshell what is your null hypothesis and what is your alternate hypothesis. Now, after framing the hypothesis, what we generally do, after selecting a research design and sample size appropriate to the hypothesis to be tested, Now, you sample size sampling, this will be, as I told you, discussed by my next speaker, my senior, Dr. Shubhanan. So he will discuss everything in detail, how to go with the how what are the ways to determine the sample size before you enter into a trial, and what research design is a different ball game altogether. So if a separate session, I think you will get through it. After that, you frame the hypothesis, as I told you, this null and alternate hypothesis you frame, and then you decide which statistical value or statistical tool you need to take. Means deciding for the test of significance, and what you are why you are doing that. You apply the test to determine the p-value. P-value means the probability value. The probability value is from the results one has observed. Means whatever result you have observed, you from that you try to get the probability value and compare with the critical value of p, which we take as researchers generally consider it to be 0.05, because it is thought that 1 out of 10, 1 out of 20 in statistics, generally it is taken that 1 out of 20 events might happen. So one event out of 20 events might happen accidentally. So that is why the p-value which we take is minimum taken to be 0.05. Means 1 out of 20 means 0.05. So if your p-value ultimately comes less than the critical value, that is 0.05, then we can reject the null hypothesis. Means the probability of accidental occurrence is not there. In other words, if I say, and your alternate hypothesis turns out to be true, means your biofertilizer is generally increasing the plant growth. It's like this. So this is the concept of p-value. So concept of p-value, it is universally used in hypothesis testing. This denotes the maximum probability of getting result observed, assuming the null hypothesis to be true. Expressed alternatively, it is the maximum probability of getting the observed outcome by chance. It depends. If the value is less than 0.05, then you are done. You have a reason to rejoice. Then your alternate hypothesis tends to be correct, or null hypothesis gets rejected because the probability chance becomes nullified. As I told you, the statisticians have agreed 1 in 20 chance of an accidental result is acceptable in the real world. And thus the cutoff for p-value is taken to be 0.05. So this is often why, what is the p-value, there are many misconceptions or maybe lack of conception. So this is a simple reason that this is a standard thing taken by the statistician, that 1 in 20 is probable accidental result which may happen in the real world situation, and hence the p-value comes taken worldwide, accepted worldwide. Critical value is to be 0.05. At certain highly significant p-values, 0.001 is also taken, that is 1%, but that is for high significant or very trials requiring much precision. But this is the standard. Otherwise, this is the standard. Next, we come to, yeah, this slide is important. As I told you, I have just seen these two, then I will explain the third part. The null hypothesis is usually stated as the population means 0 or there is no difference. However, it should have to be stated as a 0 or no difference hypothesis, which we just saw. The alternative hypothesis is usually stated as the population mean be non-zero or greater than or less than 0. So this is alternative hypothesis. Now, what is alpha and what is beta? Alpha and beta are actually, you can say, the type 1 or type 2 errors. In other words, you can say. So what is alpha? There is a probability that, obviously there are probability of misinformations, there are probability of techniques and many other reasons. So the conditional probability of incorrectly rejecting your hypothesis when it is actually true. So it might happen. There are various reasons. I'm not going into it. So conditional probability of incorrectly rejecting A0 when it is actually true, then it's obviously an error, and that error is type 1 error, that is known as alpha. And the conditional probability of failing to reject A0 when it is false. Somehow you couldn't prove that your alternative hypothesis is correct, but which it should have been, because 80 was false, but you couldn't due to some problems again. So that is beta. That is type 2 error. That is type 2 error. So, and lastly, what is the power of the test? The power of the test is 1 minus beta, which in clinical terms is the probability of correctly rejecting A0 when it is false. So the power of the test is what we actually look for, because that is what we demand. It is the probability of correctly rejecting X0 when it is false. When it is false, it needs to get rejected, and depending upon this power, your test, more the power, more is the chance of getting your alternate hypothesis as the established one. Okay, so this was the alpha, beta, and the power, and the H0 and the HA. This is the steps which I already told you, and these are the types of the problem. Comparison of sample mean with population mean, comparison of two sample means. These are the things we generally do when we take up trials. We try to compare the groups. So what we compare? We do the comparison of sample means with population mean, with comparison of two sample means. It may be a sample proportion with a population proportion you compare, or comparison of two sample proportions. These are the things we can adapt as per the trials. That's why I was telling that you go through the different published articles related with trials and see what are the statistical analysis they have adopted, what are the research design they have adopted, what was the study design, the methodology they have talked about, and see what are the type of data they have taken and how they have converted the data and which test of significance they have used. Now, the test of significance, which I will go in a very quick pattern, because these things is totally, I think, more practically if you go through the articles, or if you yourself encounter or try to do some research trial, then actually you get more practical idea out of it. Suppose you have a data set of data, and how should you represent that? How should you convert it into an analysis part, and what will be the statistical tool which is given in this two slide? Which one you will use? Whether you will use a paired T, whether an unpaired T, or a Z test, or an ANOVA. These are the criteria, which is totally based on what we have done so far. Let's go with one by one. So this is the first one, is the parametric one, where we try to use the paired t-test and unpaired t-test, most widely used test nowadays in clinical trials. And what are the things, what are the criteria? It is used to compare the two quantitative measurements taken from the same group of the individuals. So quantitative measurement, this is first point to be noted, taken from the same group of individuals. These are the things often used in clinical trial, before treatment, after treatment. So same group of individuals, that's why. Used when the following criteria are fulfilled. They are randomly you select the homogeneous sample, no problem. Quantitative data, which is either measured on an interval or ratio scale. So you use some parameters, scoring parameters, or anything, any other response parameter you take up. Variability normally distributed, and sample size less than 30. This is the misprint. Sorry. This should be sample size more than 30. Okay, next one is unpaired t-test. It is used to compare means between two distinct independent groups. It is used when the following criteria are fulfilled. Randomly selected again, homogeneous sample is quantitative data, again on interval or ratio scale, and sample size is less than 30. But here I see unpaired t-test, what? You compare the means between two distinct or different groups. And totally different groups means they are independent. Group 1 and group 2, they are totally different, having different samples, different people. So that is unpaired t-test. Z test, it is used to compare the difference in the population mean and a sample mean, or the difference between the two independent sample means. We just saw what is the formula of Z score and all that, where we deal with the means basically. So used when the following criteria are fulfilled, the sample or the samples must be randomly selected. The data must be quantitative in nature, measured on an interval or a ratio scale. The variability measured to follow normal distribution in the population. Sample size needs to be larger than 30. Population variances are known. Now, next, ANOVA. It is used to compare means between three or more distinct independent groups, but as may be used for more than two repeat measures of the same group. You can do it in the same group if you are repeating it after certain time. You can do a repeat measures as a repeat measure of the same group. You can do a no problem. Used when the following criteria are fulfilled. The samples must be randomly selected. The data must be quantitative in nature, measured on an interval or ratio scale. The variability is assumed to follow normal distribution in the population. Now, this Pearson coefficient of correlation, this is actually related with correlation, which I will come to the last after this slide. Going to it because this is also a certain thing very basic thing you can see where you need to draw the degree of relationship or association between two quantitative variables. For example, if you want to see a relation between uric acid and cholesterol, suppose you may encounter in your clinics also that there are many patients of dyslipidemia who are also having high cholesterol levels. Suppose you really want to see whether this correlation is that much effective or really it is found in a large group of population in the urban, it may be finding a more associative factor in the urban population than in the rural population, maybe. So what do? You go for this kind of test. So where you will see the parameters of uric acid, you see the parameter of lipid profile, and try to correlate using a scatter plot diagram and see using a formula. You try to see how much is the correlation. If it is less than, if it is more than 0.5, it's having a good correlation. If it is less than 0.25, then definitely it is having a very poor correlation. So like this, you can do it with convert any of your data into a proper study. So use when the following criteria are fulfilled. The sample must be randomly selected. The data must be quantitative in nature, as I told you. For example, like this one, measured on an interval or a ratio scale. The variability is assumed to follow normal distribution in the population. Okay, now we have another set that is the commonly non-parametric test. Commonly used is non-parametric in that you have the chi-square as well, is the most commonest in the non-parametric category. It is used to find out association between two nominals. See, it's now nominal or ordinal. Why? Because these are qualitative non-parametric tests. They will deal with the qualitative type of data. So used when the following criteria are fulfilled. Preferably random samples are but not necessarily. Distribution of the population parameters is unknown and non-normally distributed. These are the reasons why it's a non-parametric test. Sample size need to be more than 30. The last will be uploaded, no problem. Next, the sign test. It is used as an alternative test to t-test, where the median is compared rather than the mean. It is used to test null hypothesis about the population median with a single sample or the paired data. It is used when the population parameters are not known or normally distributed. Used when the data available are on the ordinal scale rather than interval or ratio scale. The underlying mechanism of the test is that the distribution of the variable of interest is continuous. Sign test. So article telling you, so you just find an article where they have used a sign test, and then you just correlate what are the type of data they have collected. Then you actually get a more practical idea of the things I'm not talking about. Now, median test, it is used to test the null hypothesis that the two independent samples have been drawn from the population with equal median. The following assumptions are measurements needs to be taken. The samples are independently and randomly from respective population. The populations are of same form and differ only in location. The variation of interest is continuous. Level of measurement at least ordinal. Samples do not to be equal in size. This is another important thing where we often use this because where we don't have the equal number of samples. So you can use this. Magnetic and Wilson sign test. This is also very widely used. The median test does not make full use of information measured on the ordinal scale. Therefore, the McVitie test is used for a better use of data. And median is used as a measurement for central tendency to compare the two samples. The two samples of size n and m respectively available for analysis have been independently and randomly drawn from the respective population. The measurement scale is at least ordinal. If the population variable of interest is continuous. Wilson size test, if a sample size is less than 30 and is drawn from a grossly non-normally distributed population. We don't have a normally distributed population. and the T and the Z test cannot be applied. That's why the importance of initial test. Where you have so many things which you can't do. And then you actually get an option of this readings and text. You cannot have a normally distributed population. You have a sample size which is less than 30. You cannot do T test. You cannot do Z test. It's a best alternative non-parametric test. You go with that is readings and sign test, where you have a single sample or you have a paired data, and there is a paired data. So the following assumptions: the sample needs to be random, the variable needs to be continuous, population is symmetrically distributed about its mean, and the parameter is at least in intervals. So these are the things you will use to verify your hypothesis, and then ultimately you have to go for that p-value. The last portion of the biostatistics, that is correlation and regression. As I told you, it's already clear to you that to find out whether there is a significant association or not between the two variables, we collect coefficient of correlation, which is represented by symbol R. This is the formula, and as I told you, the R tends to be like -1 and +1, depending on how poor and how good is the correlation between the two variables. Perfect positive correlation, we will have a +1 variable, both variables rise and fall in the same proportion. As I told you, suppose you have a uric acid as well as a lipid profile cholesterol, both are rising. Uric acid is also higher, cholesterol also has been higher. If that really comes as a positive correlation, then it will be highlighted in that way. Otherwise, if it's a negative correlation, then one will be rising, another will be decreasing like that, inversely proportional to each other. So it's perfect negative correlation. That may also happen in other situation where if your, for example, LDL and HDL, they have negative correlation. If your LDL becomes higher, your triglyceride cholesterol becomes higher, your HDL should be becoming lower, which is a good one, but you actually lose it. And they have actually a perfect negative correlation in that phase. So moderately positive correlation, it will be lying between, as I told you, 0 to 1. Moderately negative correlation, it will be -1 to 0. Absolutely no correlation, then it will be having 0, where it indicates no linear relationship existing between two variables. Means if you plot a spot diagram, you will not get a proper linear graph, you will get a haphazard line. It will be totally a non-linear presentation of the graph. So that is absolutely no correlation. So finally, the conclusion, which I want to say, that biostatistical techniques can assure you that the results which is found in a study are not merely because of a chance. It is really effort of some true experiment, and it has some firm conclusion and message for the society and mankind. And in every case of life, statistics plays a major role for better gaining and accurate results. And a well-designed, properly conducted study is a basic prerequisite to arrive at the valid conclusions. So this is what I want to say to all regarding the biostatistics. And I don't know the situation on the other side. I hope this is not the situation. So with all due respect, thank you. Thank you all for your patience hearing. And with this, I conclude my presentation. So thank you, sir. Over to you all.
Thank you so much, Dr. Partho Pratim Pal, for your valuable and informative presentation on statistics. And I am sure it will be very much beneficial for participants, especially those who are pursuing their MD course. When I was also pursuing MD course, and I used to think about this statistics. What is the role of this statistic? But now I can say it's a very, very important, and especially for the research work, how to collect the data and what type of the data should be collected. So it was very nice and beautiful presentation. Thank you so much. Now we have another speaker today, Dr. Subrinal Saha, and the topic is sample size. But before that, our chairperson of today's session, Dr. Atul Singh, sir, has already entered the room. So let me introduce, it's my pleasure to introduce Dr. Atul Singh, sir. Dr. Atul Singh, born on 15th December 1969, he completed his BHMS in 1993 and MD in 2003 from Rajasthan University. He also completed MBA in hospital management from Vinayaka University in 2010. Presently, he is serving as principal and professor at Dr. MPK Homeopathic Medical College and Research Center, Jaipur. Earlier, he has also served as principal at MN Homeopathic Medical College and Research Center, Bikaner, Rajasthan. He was awarded the Best Principal Award by Dr. Mahendra Singh Memorial, Kolkata. Dr. Atul Singh was also nominated as a member of Central Council of Homeopathy, where he served as a member of Executive Committee and PG Committee. He had several numbers of articles published in various journals. Dr. Atul Singh has received several awards for his contribution to homeopathy, such as repertorial in National Seminar on Homeopathy organized by CCH New Delhi, Shekhawati Hanneman Award, Appreciation Award by Indian Research Society in Homeopathy, Kanyakumari, Appreciation Award by Indian Research Society in Homeopathy, Kanpur, Outstanding Award by Indian Research Society in Homeopathy, Chitrakoot, Uttar Pradesh, Best Performance Award by Indian Research Society in Homeopathy, Jhansi, Uttar Pradesh, and many more. I request Dr. Atul Singh sir to say a few words regarding this webinar. Over to Dr. Atul Singh sir.
Thank you, Sanjeev. Good morning, good afternoon, everybody. Thank you, Sanjeev, Dr. Yesika, and Mr. Manish Jain. I welcome to all you to the fourth day of 1 week PG workshop with the them and the exploring and powering path of homeopathy national webinar on postgraduate education in the homeopathy, organized by Homeopathy Science and Congress Society and Homeopathy 360 and supported by CCRH and all PG College of India. This webinar has been thoughtful, planned to cover the subject related in MD Home course, capacity building for the PG scholar, involve them with the concept of research methodology and biostatics. Therefore, these subjects have been integral part of PG curriculum since the time of inception MD course by CCL. The need of incorporation of research methods in the curriculum was essential because the scientific evidence of the efficacy of homeopathy system of medicine need to be validated to term of modern science. Moreover, in this era of evidence-based medicine, these subjects are evidence more necessary. There is great relevance to research in education and clinical practice. PG scholars need to understand the role of scientific research and clinics, as this is one only way of stress and validity of homeopathy. Research and publication are crucial and essential to grow and prospect of the academic career. They play a valid role in the education and academic career of the researcher. Understanding the importance of science research in education will be ultimately reward and PG scholar. My best wishes for the speaker for this part, Pratim and Subramanian Shah, who will speak on the today. I also thank to Amit Nayak for the National Homeopathic Medical College Lucknow for being with us today. I hope this national webinar on the PG curriculum will be helpful to the PG scholar all over country. And also thank you for Dr. Sani sir for guiding me. Thank you, sir. Thank you very much.
Thank you so much, Dr. Atul Singh sir, for your valuable speech. Now we are coming to our next speaker,
Yes.
Dr. Subranal Saha,
Okay.
and his topic is sample size. I'm sure that the speech is going to be very interesting. Before that, I would like to introduce Dr. Subranal Saha. Dr. Subranal Saha is a homeopathic doctor with a passion for clinical researches. Currently, he is working as a lecturer in the Department of Repertory at D&Day Homeopathic Medical College and Hospital, Government of West Bengal. He has experience in designing, conducting, and publishing clinical trials in international indexed journal of which 25 papers are indexed with Medline Pub Medicine. He had graduated from Mahesh Bhattacharya Homeopathic Medical College and Hospital, Government of West Bengal in 2010, and postgraduate in repertory from National Institute of Homeopathy, Government of India, 2018. He has also master's degree in dietetic from IGNU, and his work experience 4.5 years as SRF in CCRH, Government of India, and 1 year as house staff in MBH MCH. So now I request Dr. Saha to share your experiences. Dr. Saha, over
Yes,
to
sir.
you. You have uploaded your paper, Dr. Saha.
No, sir, not now. Kindly guide how can I share my screen? Hello.
Slide button is there, no? Right side. You have uploaded yourself or from there, Homeopathy 360.
No, I have not uploaded my content yet.
Then you can share, no? You just go to the slide icon, slides icon, right side lower, right side of your screen. It is there.
It's showing webcam thumbnail position.
No, right side slide is there, no? Below the settings, attendees is there, chat, polls, offers, then
I'm
video.
running through my mobile phone only, not computer.
Through the mobile phone.
Yes, my computer's webcam is not functioning.
Just wait.
I would request the audience to please wait for a minute. We'll just connect to sir. There is some technical issue. Sir, by the time, can we discuss any queries with Dr. We discuss with Dr. Pal? Can we discuss some queries?
Yeah.
I'll just connect to Subrana.
If let me see if there any question, then we will go for that.
Hello.
Is there any question from anyone? You can write in chat box. Participants are requested, if you have any doubt, any queries, you can write in chat box. Dr. Partho is with us.
He'll join in a minute. Sir, I think there are queries. I'll just check.
I have already requested participants.
Yes, sir. No queries.
No queries.
Yes. Can I request the audience to please post your queries in the chat box? He'll join in a minute. He's mailing me the presentation. I'll just upload and Dr. Sanjeev, then we can continue with the webinar.
Yeah, sure.
I request the audience to please wait for a minute. Dr. Saha will join us in 1 minute. डॉक्टर साहा सर आपकी आपकी स्क्रीन पे एक वीडियो ऑप्शन दिख रहा होगा ऑडियो के साथ ही मोबाइल में
ऑडियो के साथ यस
उसको ऑन कर यस ग्रेट विजिबल just mail me your presentation. I will
I have already mailed. Please
do
check.
the
Please
so
check. I
I
have
not
already
received. I'll just check once again. I'll check again. Yeah, I got it. So I'll just take a minute.
See, there
By
are
the
two
time, Dr.
formats.
Sanjeev,
One
can
is
you please introduce her so that
Yeah, I have already introduced him.
sir, give me a minute. I'll just upload it.
Yeah.
Yeah, I got both the formats, PDF also and PowerPoint also.
yeah.
I will upload the PDF only because it will take less time. Just a minute, sir. It's about to upload. Sir, it's ready.
Yeah.
Can I request Sanjeev sir, please?
Yes,
Can you
yes, yes.
run it for sir?
Yeah, yeah. So once again, I welcome to all the participants, and of course, today's speaker already one speech had been completed by Dr. Partho Pratim Pal sir, and now we have Dr. Subranal Saha. Already I have introduced him, so now I request Dr. Subranal Saha, just go for that, present your experience and paper. Dr. Subranal Saha, over to you.
Thank you, sir, for inviting me and giving me this opportunity to present this topic on sample size calculation. Thanks to Bijan, Sahani sir, and my teachers who have faith on me to present this very, very important topic on sample size calculation. Uh, Currently, this topic needs special attention. Especially, I hope the audience is mostly the PGTs, and therefore, from the very beginning of PG course, this question, what is the sample size? This question haunts the PGTs, and it's my practical experience that this question is troublesome and really, really troublesome till the end. One searches for his life, what is my sample size and how to justify it. So, keeping in mind this current situation and this really troublesome situation, uh, to properly justify the sample size, I have targeted my presentation to PGTs only. So, and I have tried to make it very lucid because very easy, very simple. Because I don't want to terrify people with number of formulas. There are, I have come across more than 50 formula till date of sample size calculation. I have no intention of presenting all those 50 formula here because we need to know what is only useful to us, and not only that, we not only to learn this thing, we have to apply this thing, and this is very, very important to apply our learnings. So if we want to focus on 100 formula of sample size calculation, it may be like that you can learn a single formula or a single thing, a single approach how this whole process is done. Rather, we should focus on what is relevant, what is useful, especially being a homeopathy PGT. Kindly change the slide. I have, can I operate myself? Okay. This is
Sir, I
the,
don't think uh, I don't think there will be an option to operate. Can you see any option of previous next?
no, 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 I'm not saying.
Yes, sir. Dr. Sanjeev will do. Don't worry.
Okay, no problem, no
Yes, sir.
problem. Okay. See, I have structured
Okay,
this
okay.
workshop into several sections. First thing, why should we calculate a sample size? Next point is, what are the preliminary considerations like type 1, type 2 error, study power, and what are the deciding factors behind the sample size calculation, especially study designs, and very, very much targeted toward PGTs. See the second point, study designs in PG thesis, and another important question, sample size of single arm trial. Next, I'll be going to different calculation techniques using formula, nomograms, Lur's method, or rule of thumb. And I have given some worked out examples. I will show all these things. A little bit of mathematics, very little bit, but don't worry, don't be terrified. There is always an alternative. It's up to you which way you like to choose. Okay, so please go to the next slide. Please, next slide. Yeah. First thing is, why should we calculate sample size and what is this thing? Calculating sample size. First thing is that there are two things. One is sample, another is population. Sample is a small representative part of the population. Say, for example, a population is 1 lakh. And out of that, I'll be taking only 100 participants in my study, whatever is the kind of the study. So that 1 lakh is the population, and out of that 1 lakh, 100 is my sample. It's very as simple as that. So sample is a small thing. You can memorize it. SS, sample small, population is large. Okay. So first point is clear. So we have to draw our sample from the population. Next point is, purpose of sample size calculation is your sample should be, see the second point, neither too small nor too large. This point is of unique importance. If your sample size is too small, I have just mentioned, or my previous speaker has mentioned, a term called power, study power. Higher is your sample size, higher is the power, greater is the power. But if your sample size is smaller than the recommended or the ideal, then your study power goes down. That means your study or trial becomes underpowered. And doing an underpowered trial is having some serious ethical reasons. Why? Because, I'm repeating again, doing a study with a small sample size, or better to say, running an underpowered trial, is ethically problematic. Reason? The reason is that the results generated from such small trials are not generalizable to the population. Clear? So, say we are working with a sample, and our use of statistics is to generalize the findings to the population. We can't work with 1 lakh population. We will be working with 100 samples, and we will try to generalize our study findings with 100 samples with 1 lakh population. This is the purpose of applying statistics. So a trial with a very small sample size becomes underpowered, and underpowered trial results can't be generalized to population. This is the basic problem of running a very small trial. Second point is, your sample should not be too large, because it will cause wastage of money, wastage of time, and wastage of labor. So your sample should be very much optimal, moderate, achievable. Okay. You have to keep in mind all these things, as well as statistically justifiable. So you have to keep in mind all these things, that your sample size should be achievable, it is statistically justifiable, and generates statistically valid results. So we should not be satisfied with very small sample size, or we should not aim very high. That may cause failure. Okay, so the second point is clear. I'm coming to the third point. First thing is that sampling and sample size calculation, these two things are totally different. Please don't be confused with these two terms. One is sampling, another is sample size calculation. In sampling, we focus on selecting participants from a population, but usually sampling is done in case of observational studies only. Sampling is restricted to observational studies only. In clinical trial, we do sample size calculation specifically. So what I'm trying to say, sampling is not applicable in clinical trials. Keep it in mind. Sampling is not for clinical trials. In clinical trials, we have very strict inclusion and exclusion criteria by which we enroll patients or participants, be healthy or be patients. So In today's presentation, the topic given to me was sample size calculation. Therefore, I am not going to discuss about sampling techniques. Okay. So make it very clear, we will restrict our discussion or presentation only to sample size calculation. That means how many patients to enroll in our trial. That's all. Next, it is elaborated in the next slides. But yes, the fourth point, sample size calculation provides the number of study subjects needed to carry out the study. And without sample size calculation, research may generate erroneous result, as I have already discussed. Next slide, please. But before going into exact sample size calculation, we have to keep few points in mind. Dr. Parthapratim Pal, my previous speaker, has already discussed this thing. That is type 1 error, type 2 error, and study power. See, Dr. Partha has already mentioned this thing. Type 1 error is also called alpha. Type 2 error is also called beta. And both of these are taken into consideration while we will calculate our sample size. And 1 minus beta is the study power. What is important to remember, see, these are basic things about sample size calculation. But the point is that even if you don't understand too much of these statistical intricacies, because this type 1 error is almost always fixed at 0.05 or 5%, whatever you say. So to simplify this thing, alpha is 5% or 0.05. Next, beta is 0.80. Okay, or the study power is 80%. Okay, so from now on, we will be moving with 2 points only. That is type 1 error, that is alpha, that is kept as 0.05, and study power is 80%. And that is the minimum recommendation. You can't go below that. So from this slide, we have 2 points only. Keep in mind, because there is much complications in understanding these things. I'm not going to explain. We'll lose interest. Keep in mind only 2 points. Type 1 error is 0.05. Power is 80%. That's all. Next slide. Now, if we are going to standard any epidemiological book or biostatistics book, we'll be seeing huge branching numerous types of study designs. But to simplify this thing, see, because from the very beginning of the presentation, I am trying to make the thing simple, comprehensible, so that easy to memorize, and above all, you can apply these learnings in your real life. Okay, so sample size, the main factor to decide how to calculate sample size depends on the study design. First thing, we can classify study designs into 2 parts. One is observational, another is experimental. Under observational, see, this is important. There are 2 types. One is descriptive, another is analytical. Under analytical, there are 3 types. You already know about it: case control, cohort, and cross-sectional. And under the control trials, there are 2 types. There are randomized control trial or non-randomized control trial. So whenever we are approaching to sample size calculation, this study design should be kept in mind, because the design will say which formula to use and which one to not use. First thing is that under the descriptive studies, there are no necessity for a sample size calculation. Okay, so Next, we are coming to case control cohort and cross-sectional. All these kind of studies are related to assigning a cause with a disease occurrence. For example, smoking and hypertension, or smoking or lung carcinoma. So these kind of analytical studies with comparison group are very rare or rarest to be taken up as PG thesis. So we are not going to discuss about these things, okay? Because I have never seen, or probably will never see, any PGT, any homeopathy PGT to take up this case control cohort or cross-sectional study designs, because these are not really about homeopathy. It's about assigning a probable cause to a disease occurrence. Okay, so we'll focus our sample size calculation on controlled clinical trials only. Okay, so next slide. Yes, but while have a look at the homeopathy PG thesis, till date I have seen only there are mainly two types of studies being taken. One is single arm trial, another is control trial. Now, just to brief, single arm trials, we take a group of patients, we assign them to some homeopathic intervention, and after some period of time, we assess the outcomes. For example, group of patients suffering from iron deficiency anemia are taken. They were given homeopathic treatment for, say, a period of 6 months. After 6 months of treatment, their blood hemoglobin level, or if possible serum ferritin, is measured again. Now we compare the baseline values with after treatment values, and this type of study design, this type of trial are called single arm trials. On the contrary, there is another type where, for example, placebo control trials. These trials are being taken up by many PGTs nowadays, especially in West Bengal state colleges and National Institute of Homeopathy as well. Control trials where a group of two groups of patients are taken, where one group is given medicine and another identical group is given placebo, indistinguishable placebo. And this intervention, both medicine or placebo, is continued for 3 months or 6 months, and the outcomes are measured again. Now we compare the findings between these two groups. Okay, so this is the basic difference between a single arm trial and a control trial. Control trial, in control trial, there is a comparator arm. It may be placebo or any standard comparator. Okay, so these two types of studies are taken by almost all the PGTs across India in homeopathy. Okay, so if we are going to calculate, how to calculate a sample size of this single arm trial? See, this is the formula: Z alpha plus Z beta whole square into sigma square whole divided by delta square. Now, what are these things? See, Z alpha, Dr. Partho has discussed, and I have already mentioned, it is the level of significance kept at 5%. Z beta, it has a fixed value of 0.84. Okay, so don't be very much stressed about these terms, because these are fixed value that you will be supplied with. Z alpha is 1.96 and Z beta is 0.84. Okay, solved. Now, what is sigma? Sigma is standard deviation. I will show you in the next slide in another example. So sigma is standard deviation and delta is the clinically meaningful difference. For example, if I am trying to treat iron deficiency anemia, see, focus on it, that if a person's hemoglobin level is 10, for example, if we can increase it up to 11, then there is a clinically meaningful change that may occur in the patient. Okay, I'm repeating again. A patient is suffering from iron deficiency anemia and his hemoglobin level is found to be 10 gram per dl or 10 gram per cell. Now, if we can increase it by 1, that is up to 11, it may occur that a clinically meaningful change may take place in the patient. So this is the delta. Please go to the next slide. I am going to elaborate this example. Yes, see, that is an example. A homeopathic physician, it is a perfect PG thesis. Almost 90 to 95% PGTs take up this kind of trial. Okay, what is written? A homeopathic physician wants to know if the mean fasting blood glucose level in patients suffering from type 2 diabetes can be changed after treatment with individualized homeopathic medicines. Okay. Now, he considers a mean difference of 8 gram per dl to be clinically meaningful. What I was telling in the previous slide, you are assuming that if you can reduce the blood sugar level by 8, then it may produce some clinical change, beneficial change in the patient. So you are assuming it to be 8. Okay. Now, he also chooses 12 as the variation expected based on a previously published study. What it means? It means that in any previous trial, not necessarily in homeopathy, it may be a prevalence study, that the standard deviation of the diabetic population in fasting blood glucose level was 12. Okay, it means that 12 is the standard deviation. Now the question is, how many patients will he need to carry out the study with significance level of 5% and power of 80%? See, if it is a single arm trial, this kind of studies are taken by PGTs. Now, before start of the trial, suppose the PGT aims to calculate the sample size. How to do? See, from the very beginning, I have asked you not to be stressed about this Z alpha and Z beta. See, it is already supplied. Z alpha is 1.96 and Z beta is 0.84. Okay, but keep in mind, it is Z alpha 1.96. This value is applicable at 5% significance level. If the significance level changes, this value will also change. But don't worry, the value will be supplied to you. And Z beta, it is kept as 0.84. It is also applicable when the study power is 80%. Again, don't be worried. If the study power is not 80%, it is, for example, it is 90%, then the Z beta value will be supplied to you. Okay, so there is no concern about Z alpha or Z beta. These two values are in our hand, 1.96 and other is 0.84. Now, the standard deviation as given in the statement, that is 12. See, sigma is equals to 12. Now, and ultimately the delta, what is the difference we are wishing to detect? That is 8. It is also supplied. So, see, you have nothing to calculate. All these values are supplied to you. Z alpha, Z beta, sigma, delta. All are given in this question. Just put these values in the formula. You will get the sample size of 80. Clear? So this is the formula by which almost 95 to 99% PGTs in India who are taking up single arm trials as their PG thesis, they can calculate their sample size. Okay, I don't think that it is too much complicated. See, because all the values you will be supplied with, you just need to put that values in this formula. Okay, next slide. But this is another magic number, sample size of 30. I have been hearing this since last 15 years that your sample size should be 30 at least. And but till date, I have not found anyone to justify or clarify this thing. Why a sample size of 30 should be taken? The simple answer and the simplest possible correct answer to this question, why is sample size 30, is central limit theorem. Okay, what this theorem says, I will not go into again these technical or statistical terms. For your easy understanding, the central limit theorem tells that higher is your sample size, it tends to assume a bell-shaped normal curve, as Dr. Partha has very beautifully illustrated. Higher is your sample size, it assumes a bell-shaped or normal distribution pattern. And usually it has been seen that as soon as your sample size reaches 30, the curve takes a normal shape, that is a bell shape. And as soon as it takes a bell shape, your data becomes parametric data. You can use statistical tests accordingly. Okay, so if anyone ever asks you, what is the justification behind reaching a sample size of 30? This is a magic number. No, it is not a magic number. You simply state the answer. It's the central limit theorem that asks to achieve a minimum sample of 30 so that the distribution of the sample assumes a bell-shaped pattern or parametric patterns, so that parametric tests like t-test, likewise, just like Path has discussed, this can be applied as to draw any statistical inference out of my study. This is your answer for sample size 30. Hope I am clear. Next slide, please. Yes, I have highlighted this thing. Never forget the theory. I am not going into the theory of central limit theorem. It has several different parts. I am not going to discuss. I am discussing only what is applicable for you, keeping in mind the audience profile. That central limit theorem is the justification of sample size 30. Okay, next slide. Now we will be coming to sample size calculation for controlled clinical trials. And I don't know whether you are getting interest or not. One question is solved for your lifetime, that is sample size 30. But in today's presentation, I think this is the most important slide for doing any sample size calculation for any control trial. That means you are having a control arm. First thing is that you have to see whether your trial is, what is the nature of your trial. Is it a pilot trial or a definitive trial? See, the name itself suggests pilot trials are aimed at testing the feasibility issues only of running a larger trial. Okay, so pilot trial, the results of a pilot trial should not be bothersome. Be it positive, be it negative, it doesn't matter much. So actually pilot trial explores the feasibility issues of conducting a larger trial. For example, I am intending to take up a trial with diabetic patients with 150 or 200 sample size, for example. But before running that large trial or a multicentric trial, I want to make sure that everything runs fine. Be it recruitment, patient follow-up, outcome assessment, data extraction, data analysis, how much time it is consuming, what is the dropout rate of the trial. For addressing these feasibility issues, we need to run a pilot trial before doing any large trial. It is as simple as that. Just like your mother is cooking in the kitchen, she just tests the things. before serving you. It's just like that. If she found anything problematic, she had some sugar or salt or whatever. Before serving the food to your plate, she herself tasted, and this is what is we called as pilot trial. Okay, and this pilot trial will tell you what is to add, what is to deduct, and what are the adjustments to be made for a definitive. Okay, so for example, your pilot trial is with only 10 or 20 participants, but your definitive trial is with 200 participants. Okay, so while doing a pilot trial, this is important. You need not to calculate sample size. Okay, but but the data generated from pilot trial will be used in the calculation of a sample size for a definitive trial. This is where the importance lies of this discussion. Keep it in mind, keep it very clear. Pilot studies do not require any sample size calculation. Pilot trials are aimed at only addressing the feasibility issues of conducting a large trial. Whereas the data derived from the pilot trial are used for sample size calculation for a definitive trial. Okay, so the sequence is like that. First, you should conduct a pilot trial, get the data. With that data, calculate a sample size for a definitive trial. Okay, now, nature of the outcome. Before going into sample size calculation and applying some formula or some techniques, we should know what is the nature of our outcome measure is. For example, if you are measuring blood sugar, for example, or you are measuring blood pressure, or you are measuring blood hemoglobin, whatever it is, or you are measuring lipid profile or thyroid profile or whatever. See, these values can be presented in terms of these values are can be presented in terms of mean or standard deviations, as Partha said, or median or quartile ranges. That means these are quantifiable variables that you can quantify. These are continuous. And the second option is, for example, you are trying to achieve 20 gram reduction in the blood sugar level. Now, after the end of the trial, for example, you enrolled 100 participants, and after the end of the trial, you want to see how many patients have achieved that 20 gram of reduction in blood sugar, in fasting blood sugar. So, for example, out of 100, you have seen that 50 patients achieved 20 gram reduction of blood sugar. So, you tagged those 50 patients as improved, and the rest who have not shown that kind of improvement, you tag them as not improved. Okay, this is also commonly done in PG thesis. So these are termed as binary outcomes. Okay, or dichotomized outcomes. You are dichotomizing the outcome as improved and not improved. See, it is optional. You can keep the reading outcome as either continuous as it is, otherwise you can convert it as binary. But whatever outcome you will be using, be it binary, for example, you are saying that 50 patients have been improved, 50 has not improved. Your outcome may be like that, or your outcome may be like that in a continuous pattern, like you want to see how much mean reduction you can achieve after 6 months of treatment. So here your outcome is of continuous nature. Okay, I hope I am clear. So nature of your outcome will decide which formula you are going to use in sample size calculation. Clear? Very easy points. So I have discussed 2 points, pilot trial and definitive trial. We don't required to calculate sample size in pilot trials, but data generated from pilot trials will be used in calculation of sample size for a definitive trial. And the nature of outcome, whether it is binary or whether it is continuous, this will decide which formula or which technique we are going to apply. Next, another important part, your existing literature on that will help you to sample size calculation. For example, I am going to run a trial on hypertension. Now, the first thing is that we have to identify any similar study is already published or not. First thing is that you need to identify similar published research literature, whether being a homeopath, I am going to run a trial on hypertension. But first of all, I have to search whether any similar study has taken place earlier. If yes, okay, if yes, then I have to get the full paper. I have to check the PICO. What is PICO? That is P for patient, I for intervention, C for control, O for outcome. Whether that earlier published paper or trial has similarity with mine in these terms. That means the patient which I am planning to work with, the earlier paper, in that paper, whether the authors have enrolled similar patients. For example, I am trying to work with adult hypertensive patients, but the earlier paper has worked with geriatric hypertensive patients. So you can't use the data generated from that paper into your trials sample size calculation. Clear? So if you are working with adult patients, you have to see whether the previous paper is also enrolled, has also trial was conducted on adult patients only. If it is on geriatric patient or some other population, that data can't be taken in sample size calculation. Next is intervention. For example, the earlier paper, they have given baritamide 3x to all the geriatric hypertensive patients. But you are planning to give individualized homeopathic medicines to adult patients. See, the intervention is different. Okay, so you can't take that data in your sample size calculation. Okay, so PICO, P and I completed. Next is C, control. In the earlier paper, you see that they used one allopathy control arm, okay, where standard antihypertensive drugs were prescribed, but you yourself plan to give placebo. So again, that study can't be helpful in your sample size calculation. But another thing is outcome. That study has used, for example, any binary outcome, but you want to check the continuous outcome. That study, the earlier study, has evaluated how many patients has improved and how many not. But you want to check the exact mean reduction of blood sugar or blood pressure, whatever it is. So whenever you are planning to do a sample size calculation from a previously published study, you need to check on these things. Who are the patient? That means the patient profile between yours and the earlier study. What is the intervention? Whether the same intervention you are using. In this example, they have used baritamide, but you are going to use individualized homeopathy. So these are not compatible, not same. Third point is, what is their control arm and what is your control arm? Is it same? If so, then use. If not, then don't. And what is the outcome? Okay. Another important point to add, what is the time duration? What is the intervention of the study? If the earlier study, in the earlier study, if they have given patients 1 year long follow-up, but you are planning to give only 1 month follow-up, then it is not possible that that study data will be helpful in effect size calculation, in sample size calculation of your drug. So while using data for sample size calculation from any external source or earlier published literature, you have to be very much cautious about this thing. So pico is the point. Okay. Now another point is effect size. Is it calculable? How is effect size calculated is described in our next slides. Type 1 error, I have already specified it as, keep it as 5% unless otherwise specified. Occasionally it is specified as 1%. Again is type 2 error, that is the power that is minimum 80%. And usually the allocation ratio is 1:1. That is, it is usually taken. But if it is 2:1, for example, you want to give 200 patients medicine and 100 patient placebo, in that case, some adjustments need to be done. Another thing to decide your sample size calculation is whether your test is one-tailed or two-tailed. This is very tricky. When you are very much confident that your medicine is not going to produce any effect inferior to placebo, then you can take one-tailed test. Otherwise, it is always preferable to go for two-tailed test. Whenever you are using one-tailed test, your sample size will be comparatively lower than the two-tailed test. Another point to mention, that is outcome measure. Usually, it is very, very important. Sample size is calculated only on the primary outcome measure. Okay, not on your secondary outcomes. So, but the problem is when your study has multiple primary outcomes, what to do then? You have to calculate sample size for each of your primary outcome measures, and you have to take which one is the highest one. For example, for a primary outcome measure, your calculated sample size becomes 100. For the second primary outcome measure, your calculated sample size comes to 120. And the third one, your sample size goes to 150. You have to take your sample size as 150 because that will cover the other two also. Okay, so these are the basic considerations before jumping into formulas or any techniques of sample size calculation. Next slide, please. Yeah, this is the formula. Nothing much to explain. I have already explained these things. A and B, these are alpha and beta. Clear? See, alpha 0.05, beta is 0.80, 80% power. What I am saying. Sigma is the standard deviation. I have already said. Mu1 is the mean in the group 1, and mu2 is the mean in group 2. See, all these values will be either extractable from the paper, published paper. If not, then you can't calculate sample size. And if it is in your exams, all these value will be supplied. Okay, so don't get stressed about these things. I will be showing you on an example. Give the next slide, please. Okay, yes, the earlier one was about formula only. Now there is another way out where you need not to memorize that formula, but use one Altman's nomogram. It is called the nomogram method or nomogram technique. But before going to nomogram, you need to calculate a simple effect size. Okay, or it is also called standardized mean difference, SMD, or it is also called the effect size. Sorry for disturbance. So I have shown you one formula to how to calculate sample size directly, but here is another way how you can bypass that formula without memorizing that. Okay, but Before going into this technique, Altman's nomogram, you have to memorize this formula, that is mean 1 minus mean 2 divided by pooled standard deviation. Next slide. When this standardized mean difference or effect size is calculated, you have to just put it here. This is the Altman's nomogram. I have given you the reference. See, there are two axes. In the left one, you put that standardized mean difference or effect size, whatever you say. And in the right axis, you put the study power. Okay. And in the middle, see, there are two axes. One is for significance level 5%, another is for significance level 1%. Whatever is given to you or supplied to you, you need to take that one. How to do this thing? In the previous slide, I have shown how to calculate effect size. Put your effect size here. For example, in this example, the effect size is in between 1.3. See, 1.3. And in the right axis, study power taken as 0.80. Now take a simple ruler, draw a straight line, and see where the straight line is cutting the axis. Where the point where it cuts the axis is your target sample size. It is a very easy process, but before doing that, you need to keep in mind that your outcome should be continuous in nature, and you have to calculate the effect size of standardized mean difference by mean 1 minus mean 2 divided by pooled standard deviation. Okay. Next slide. Next slide, please. Next slide, please. Please change the slide.
Next one.
Has the meeting ended?
No, we have another 5 minutes, Dr. Saha. So kindly sum up your session, no?
But I can't move on. The slides to be moved.
No. Yes, I can move. You just tell me, no, at what slide we have to reach. Next one.
Next one.
You want next one? Just tell me. Next.
It's not showing here.
No, next slide or previous slide.
Next slide. Next slide.
Next is thank you. So previous one you want?
No. There are a few more slides.
No, just tell me which slide you need. Hello.
Yes, sir, you audible.
Dr. Saha, I think he has left the room.
No, he joined again, I think.
Okay.
Let's see. I request the audience to that you can mail us the queries. We'll try to connect to the speakers and then solve your queries.
So now what to do?
So we can wait a minute. Let's see. जब तक है तब तक. Hello, sir. Did he join? I think there is some issue with his network.
Yeah, network issues there.
He has joined. He has joined
Yeah.
again.
Yeah.
Sir, does Dr. Saha, sir?
Again, he left.
He left again.
Yeah.
Again. I request the audience to please post your queries to us at webinar@homeopathy360.com. We'll try to connect to Dr. Saha as well as Dr. Pal. And even we can organize the webinar of him again. Don't worry, we'll be continuing this part.
Is it closed?
No, yeah. You may go ahead, Dr. Saha.
Yes. But I can't see the slides.
Dr. Sanjeev sir, can you please wrap up the session?
Yeah. We can do that. So thank you so much, Dr. Saha, for your valuable presentation on sample size. And very nicely, you have differentiated sampling and sample size collection. So thank you so much. And now it's a time to vote of thanks. I thanks all the participants and all the speakers of today, the chairperson and co-chairperson. And a special thanks to Dr. Sahani sir, the man behind scene, and of course Dr. Yasika. Day night she is working for organizing all these webinars. No, every day she is working for the webinar, and of course Mr. Manish Jain, who had provided us a very nice platform to explore the homeopathy. So thank you so much to all of you. And now I ask Dr. Yasika to announce tomorrow, the program. And
So I
will
just
then
want
sum
to
up.
announce that tomorrow we are having the session again at 11 o'clock. We'll try to start it on time. So I hope you all will be there with us tomorrow again. Thank you so much. For any
Thank
queries, you
you
can
so much.
mail us at webinar@homeopathy360.com.
Yeah.